Hello again, everyone. Thank you for joining Mauser and Samtec for this webinar. My name is Mark Patrick. I'm Director of Technical Content for Mauser Electronics here in EMEA. And joining me today is Matt Burns, Global Technical Marketing Director for Samtec. For those who might not know Mauser, we're a global distributor of the newest semiconductors, passives and connectors from over 1,100 manufacturers. And we stock around 30,000 individual Samtec products. So if you're inspired by today's webinar and want to investigate Samtec's solutions further, we have whatever components you're going to need in stock. So with that, let me hand over to Matt.
Thanks, Mark. Great to be here with you. It's always a pleasure to work with Mauser, such a valued partner for Samtec. And more importantly, we welcome our listeners and our attendees from around the world. We really look forward to our hour together. And as Mark mentioned, I love interactive presentations. So if any of the listeners have questions, please ask those during the chat and we'll answer real time. This thought process of signal integrity in embedded systems may seem like it's not a factor, but from Samtec's point of view, it's just the opposite. And really why we see an increase of focus on signal integrity is because of the fact that global systems are getting faster, right? And when you look at some of the trends that's driving performance, a big topic behind a lot of this is just the global advancement of artificial intelligence. You'd be hard pressed to come across someone that doesn't know what AI is, mainly because of ChatGPT. I shared an experience with another presentation I made a few weeks ago, that I have extended family members who are some of the least technical people in the world that don't understand electronic components, but they understand what ChatGPT is because they can get the output that they're looking for whether it's making biscuits or trying to find their favorite TV show. So the fact that the public's awareness of what AI can do is only going to drive more and more innovation in that space. And for the embedded community, how are we going to put AI at the edge? Obviously, AI is revolutionized how data centers work because of what NVIDIA's done. But really, the next edge of performance is at the edge, which is mainly embedded type applications. In addition, we continue to see the growth of 5G connectivity, 6G connectivity, autonomous vehicles, and a number of the digital technologies that our modes of transportation have, plus just the fact that we've got mobile technology everywhere we go, is really driving what Samtec calls a technical renaissance. It's not only the progress in our day-to-day life, but the technology behind it that's driving it. And for our world, when we're talking about signal integrity, we're really seeing the interconnect industry going from, over the last 10 to 15 years or so, the interconnect industry, including Samtec, going from a follower in terms of performance, right? You think back to the 90s, there was the megahertz wars between Intel and AMD in terms of who had the fastest processor. But now it's almost, the question's almost become, who has the fastest connector? And if you look at the industry solutions from Samtec, as well as some of our competitors / frenemies, you'll see that our portfolios can support bleeding edge 224 speed. So it's really about, I've got a piece of silicon, how do I route the data between that? And that could be a board-to-board connector, that could be over a cable, that can be an RF connection, that can be optical. So we'll cover some of that at the end, but I just want to lay the framework, Mark, about why we're so interested in SI and embedded applications.
Yeah, just a quick question, Matt, because I think you'll probably address it as we head further through the presentation, but somebody's asking about board-to-board connectors specifically, but not kind of the bit rates you're talking about, one megabit per second. So I'm sure you'll come on to something like that later in the slides, right?
No, and I think this question from Pavel illustrates the point of this illustration. So the answer is yes, we've got lots of solutions for that, Pavel, and I'll talk about that more at the end.
Excellent.
But in a data center world, we're thinking that 220 right now, 56 112, 224, that's kind of where the data center world is, because that's bleeding edge high speed performance. But for the embedded audience, making that jump from 100 kilobit to a megabit, or from 1 megabit to 100 megabit, or even going from let's say 1 gigabit Ethernet to 10 gigabit Ethernet, which is happening in a lot of industrial control and embedded communications.
Yeah,
that's a design challenge for a lot of folks. And the same SI techniques that we're going to talk about in this presentation that bleeding edge designers from hyperscalers, those same techniques apply in the embedded space. So, going back to the presentation, this slide just kind of gives it a high-level overview of all the interconnect solutions that Samtec offers, from front panel to backplane, midboard, RF, optics, et cetera, which really drives the need for signal integrity, whether it's going from your main chip on your solution to the connector right by it, or from the main chip to the front panel, or the main chip to the back panel on the back. So signal integrity covers all those domains: copper, RF, optical, and we will talk about those as we go forward.
It's interesting you mentioned ChatGPT as well. And we think about the infrastructure that's required to make a service like that available. And going back to your previous slide, data centers. So the people who are not aware of the technology and how it actually happens, they're experiencing it nevertheless.
No, and you make a valid point along that, Mark, too, in that, ChatGPT, I did a little bit of research on this because I'm just curious, right? ChatGPT by itself is about a 650 gigabyte application, the data set and all the instructions that come within the AI model. And that may not sound large. You're like, I thought, well, I can fit that on my laptop, because my laptop has 2 or 3 terabytes of hard drive space, depending upon the model you get. So personally, I could run ChatGPT on my laptop. But if you try to scale that for tens of millions or hundreds of millions of users, now you're going from one GPU, one NVIDIA GPU, to 10,000 in one data center. And then you have to scale that data center to, there's something like 10,000 data centers around the world, plus or minus.
Yeah.
So it just illustrates the need for SI, right?
Yeah.
Now, I'm not saying you're going to put ChatGPT on your smartwatch, because that probably doesn't make sense, right? Who knows? Maybe the voice commands go back to the cloud connectivity to use it that way. But there are 8-bit, 16-bit, 32-bit microprocessors, SoCs, that are available from Mouser that can run AI on it. Yeah. So there's still, or whether it's a smartwatch or a smartphone or a smart blender, right? That's kind of where we're driving with this technology. So,
sorry, I hijacked it. Let's move on.
That's a good question from Peter. We're getting a little bit off topic. We're going to get back to SI, but ChatGPT, I think, focuses on why we need SI. So when looking at this presentation, whatever your application is, it illustrates the need for signal integrity. So whether if you're in the embedded world working at 1 gigabit, or if you're data center working at 224, you need an open eye, right? If any of you are Transformers fans, sorry, I watched the movie recently with my daughter. We had a laugh about Optimus Prime saying more than meets the eye. That's why I put in this presentation. But if you have an open eye, everything looks great, right? The illustration on the left shows the boundary scans in terms of where the voltage of the level, in terms of the voltage of the signals, where it can pass through. When you're, this is at the transmit side, and hopefully on the receive side, this is what your receiver sees electrically. If you look at the eye diagram on the right, if your receiver sees that, you're in trouble, right? So what are some of the specifications, or what are some of the parameters that go into affecting that signal? Whether you're running at 1 megabit, 10 megabit, 100 megabit, or 224 in the data center. So we're going to spend the rest of our presentation kind of going around that. So when Samtec looks at signal integrity from a channel standpoint, we really start to look at it holistically, right? We talk about silicon to silicon. And the table here really shows how it's not just one component along that signal chain that affects the signal integrity of the entire channel. So a customer comes to us and says, I need to run, I'll use Peter's example, or Pavel's example earlier. I need something to run 1 megabit over my connector. Okay, that's easy. But if Pablo comes to me and says, I need to run 50 megabit over a connector, then the question becomes, well, okay, how far is your silicon away from the connector? What type of PCB material are you using? How many vias are you going through? Are there any cables in between there? So it really helps us to see that from an SI standpoint, we look at the transmit die, we look at the package of the IC, we look how those traces leave the bumps through the PCB, how many vias, PCB traces, et cetera, what type of PCB material, FR4 versus something along the lines of a tachyon or something along those that. The connector BOR or breakout region, which is how the signals are pinned out or break out from the signals, the connector itself, and then the same on the receive path. Here we show a coplanar application, but this same type of holistic approach could be board to board, vertical, right angle, cabled, whatever the case may be.
So it's end to, again, I think like a lot of systems, you have to look at it from an end-to-end perspective.
Precisely. And if we don't, we can say 50 gigabit works on our connectors because we're going that far IC connector IC. But if you're going, a quarter meter, 25 cm on a PCB, 25 cm on a PCB, it's not going to work, right? Especially if it's FR4. So we'll talk about some of the mitigation techniques that are available and some of the solutions we offer to help that. So the presentation, we start to look at, we tend to think DC, or at least I do. But when you're talking about high-speed data rates, it's really in the frequency domain. And each of those high-speed digital signals, when we think about a square wave, there's a lot of frequency in it. And the reason we focus on that is trying to understand what the Nyquist rate is. So if we need to send a 100 megabit signal, that means we have to have, to carry at least at a 200 megahertz clock rate. Frequency rate being twice the bandwidth. It's simple. It's simple Nyquist. If any of the listeners have electrical engineering background, you probably learned this to your third or fourth year of university in your signals and systems. And the idea is to make that most of the signal energy is at Nyquist. If it's below or above, it can affect the signal, right? Something else we also look at in terms of SI is what's the rise time. There's a direct correlation between how fast the rise time is and the number and the bandwidth you can get through the system. And then obviously we also are concerned about noise. In the SI world, we always want to maximize SNR, right? Signal noise ratio, specifically on the receiver side. So how can we minimize noise or take advantage of the channel that we have to get as much data through there as well? So the noise obviously is any amplitude or frequency component that you don't want. And all of these three components go into creating the noise budget across the entire channel. So, again, I'll go back to the example. I need to pass 50 gigabits over my connector. I can only handle 2 or 3 dB of loss at my Nyquist frequency, which if you look at the frequency domain versus time domain, the Nyquist frequency is half the data rate. So if you're transmitting at 50 gigabit, what's the noise at 25 gigahertz? And that's kind of where we have to look. So we'll talk about that more as we go forward, but this at least sets the stage for the presentation. Again, this may be basic, but we run into this a lot based on some of the questions we see at Samtec, the difference between single-ended and differential. Single-endeds are point-to-point communications. It requires a ground reference, as the illustration shows, typically a driver and receiver with a direct connection to ground. This is great for a lot of lower speed signals or control lines. And again, at lower data rates, the normal electrical characteristics are okay. Some of the single-ended are obviously very popular. When you look in the embedded world, coax express, SDI, RS-232, we still see a ton of I2C and SPI, especially for control for devices or IO or whatever. RF is typically single-ended. So again, it's necessary to understand these. But if you try to send a signal tens of gigabits over single-ended, it's prone to noise, right? Just because common mode, et cetera, et cetera. So, as you get into higher speeds, we get into differential pair signals, or DP as the industry calls them. DPs were introduced to create coupling. on immunity on the transmission lines. By having that differential pair, that helps to get rid of the noise. There's the drawback. It requires 2x the amount of conductors. So when you look at transmit, obviously there's a TX plus, TX minus. When you look at receive, there's an RX plus, RX minus. And you can see, whether you have, the sources go to show you can send positive and minus there as well.
Yeah.
So when you start, sorry. Oh, sorry.
No, please carry on.
My bad. So when we talk about this common mode rejection or this common noise rejection, what are we talking about? Because both positive and negative signals are transmitted, there's a net current of 0. So no return line is required. Obviously, there's a system level ground that the signals are referenced to, but for the channel, it's not needed. We talked earlier about the advantages of rejecting common mode noise. The illustration helps to see that any noise on the system is removed just because of the end transceiver topology. So the differential modes can intensify each other. The common modes are rejected. And because of the structure of these systems, we'll see, instead of saying differential pair TX plus, we tend to think of the two signals TX plus, TX minus, RX plus, RX minus as a pair. So you always see the pair mated not only mated together, but also routed together through the PCB and more importantly through connectors. When we start to talk about some of the interconnect solutions that we have at the end of the presentation, we'll show how routing those differential pairs close together through a connector not only helps with grounding schemes, but also improves performance within the system. Another technical concern that we have with is matching. The illustration on the right talks about how we want to match the source with the load so that allows for the maximum amount of power passing through the system. A good example here is an RLC circuit. The load is going to have not only some sort of resistance. It's also going to have an impedance, function to it, especially in the frequency main. So you can tune the LC circuit so that the impedance of the system in the frequency domain matches the impedance of the input. And by balancing that impedance, that helps us to minimize or, in a utopian world, eliminate the mismatch so that we don't lose signal through the system. Now, in the real world, we'll talk about how to minimize mismatch because it's impossible to have perfect mismatch when you have transitions through a system, especially when you're going chip to PCB to connector. There's all those electrical transitions can be a mismatch, and that can cause significant issues, or it may not. So we'll talk about that going forward. This just goes to illustrate, from a presentation standpoint, what can happen when you have mismatches in a system. When measuring impedance, you can see where the mismatches are on the circuit. We use a technique called TDR, time domain reflectometry. Any reputable signal integrity lab is going to have a TDR statement. And just like the name inflects, you look at how the resistance of the system looks by sending a pulse down the line and then bringing it back, and then by measuring that pulse, you can look at where you see the mismatches. In an ideal world, we try to keep the TDR as flat as possible, but no system is completely matched perfectly from an impedance standpoint. So if you look at the illustration on the left, that's a typical TDR of a typical PCB system. One with a trace at 85 ohm, other with 100 ohm trace. And you can see by looking at the TDR reflections, transitions within the system. So it's not wrong to see TDRs that aren't flat, but we want to make sure that when we do have the differences, that it's at the spaces and the times and the locations where we want them to be, and then also some of the SI techniques in terms of IL and RL, which we'll talk about here in just a few minutes, about how to minimize that going forward. The TDR plot on the right is just looking at a connector pair from Samtec, our Novaray connector series, which is available through Mauser. And all this is looking at is the electrical signal from when the male Novaray mates with the female Novaray. And then you look at the TDR of the contact, literally the contact on top of each other. So this looks a lot smoother than the TDR plot on the left because you're looking at things from a system level PCB traces, whereas here we're just at a contact standpoint.
Yeah.
So you know, and then we look at it from a you know, from a different. Not only is it an impedance mismatch, but it's also, you know, the rise time of the signal and how that affects the performance of the system. So it shows, you know, it shows that from a system level, we want to minimize we want to minimize impedance mismatch, and we also measure it with TDR, and we can look at how the impedance can change based on rise time and frequency within the system. So it's one of many parameters in an SI engineer's toolbox to see how a system is operating.
Right. Yeah.
Okay. So the next parameter we want to talk about is insertion loss. Really is the total amount of power through a component expressed in dB. Another way of saying this is attenuation, but you know, we learn about attenuation in physics and in the real world, but the electrical standpoint, especially from an SI engineer, we talk about insertion loss. It's typically a negative value when you look at it holistically, but it's usually expressed as a positive value. When you look at it from a port standpoint, as illustrated below, and especially from an S parameter standpoint, S21 is the typical desired S parameter for insertion loss, and it's normally equivalent to S12. We showed that screen image earlier of how the eye diagram had been degraded because there was too much noise in the system. And insertion loss is one of the biggest contributors to overall system loss because it can lead to bit errors within your channel when the transmission voltage gets too low, especially, or the receive path, either way. When we think about insertion loss, there can be a number of contributors, especially from power loss. We look at reflection loss, which is due to mismatch, which we talked about.
Yeah.
There can be coupling or radiated loss, which can be attributed to crosstalk when you have too many, you know, transmit receive lines next to each other, or EMI from another part of the system. You can have dielectric loss, which is you're going to have in any real world system because every system has a dielectric constant. And then the conductor loss is, you know, energy loss along the trace or along the wire.
Yeah.
So again, insertion loss is the measure of all power loss along the transmission line. It's one of the most important parameters that we use within the SI world to define how a system is going to operate and how we can mitigate that as time goes on. You know, so the question comes up is how much insertion loss is good for my system? And the answer is going to be, it depends whether your system is a signal that's about that long or that long. So, you know, some argue that insertion loss for a good channel is 5 dB, and that may be the case. It really depends upon the channel design. On the other hand, if you're looking at high-speed communications when it comes to PCI Express, CXL, fiber channel, you know, typically you're looking 30 to 35 dB, and that's, you know, from chipset to chipset, you know, chipset transceiver to chipset receiver. The two illustrations on the right kind of show that. So if you look at the graph on the right, you'll see that, you know, except for that resonance around 9 to 10 gigahertz, that connector has pretty decent insertion loss all the way out to about 13 gigahertz. It's a little bit noisy, you know, depending upon how you route the signals through the system.
Yeah.
Optimal horizontal talks about, you know, running along. If you have a long connector, you know, several of our connectors, you know, are hundreds of pins. So you may have 10 rows by 40 pins, which is a typical FMC connector that you'd find in an FPGA application. So do we optimize the transceivers along the horizontal axis of the connector, or do we optimize them along the vertical axis of the connector? That shows how all the variability that you have within the system, Mark, that an SI engineer has at his disposal in terms of how to pick pin out, how to pick the connector, how to pick the layout through the connector. So, and then when you look at the solution on the bottom, you'll see that, when you look at the 1 dB loss, now you're all the way out to 30 gigahertz. So, when I look at the insertion loss of the connector on the bottom versus the insertion of the connector on top, just looking at insertion loss, I can probably get 60 to 65 gigabits through the accelerate connector that we have on the bottom versus the Q series that we have on the top. And that kind of makes sense because the Q series is an older solution that we came out with probably about 15 years ago. And as we've learned more and more about SI, we've been able to redesign the systems, redesign the breakout regions, pick the right performance of the PCB to get better performance. It also
different demands from customers, I guess, too. As you said at the start, as frequency, data transmission rates have gone up, you're being presented with different demands from customers, which drives the innovation, right?
Exactly. And it's not only from the interconnect side, Mark, but it's also on the semiconductor side as well. PCB substrates, kind of goes back to that whole slide we showed in terms of how we look at the channel and the SI from a holistic standpoint. So we may keep, we may have short losses, and short insertion loss maybe due to match. For longer channels, insertion loss is basically just typically due to attenuation at the channel level. This also helps us to see how we may see rise time degradation in the system if we have too much insertion loss. The input, we see a rise time of 37 picoseconds. And the output is 116 picoseconds. So we see, and that's really at the input, you're closer to the transceiver. At the output, you're farther from the transceiver. So too much attenuation affects rise time, which affects bandwidth, which affects data rate. So this is just one data point to help us keep in mind that in most cases, we want to try to keep that insertion loss as minimal as possible. There's a max noise budget in terms of how much insertion loss the system can handle, the channel can handle before you start to see degradation within the system. So return loss is another key parameter that we look at from a signal integrity standpoint. It's the amount of energy that's reflected. Another way of thinking about it is if I'm looking at you virtually, Mark, a lot of my voice is being projected in the microphone, which enables you and all of our listeners to hear it, but not all of the projection from that system is getting through the microphone. One of the commenters talked earlier about how there's a little bit of an echo. That's return loss in the auditory world, right? So some of that noise is being reflected from the microphone, unfortunately being bounced off the walls in my office. Electrically, we try to get rid of that as much as possible. Caused by impedance mismatch, which in turn are discontinuities, right? You think about the trace length, transceiver, wire bond, substrate to the package to the bump to the PCB. Each one of those transitions can have return loss. And then when you look at that over the entire system, it's going to be there, but how do we minimize it, right? When you look at it from a network standpoint, as the illustration shows, it's S11, S22 from an S parameter standpoint. There's a mathematical formula that defines return loss. It's the 10 times the log of power in versus over power reflected. As a general rule of thumb, we'll talk about this a little bit earlier. You can see the return loss on the top of our Accelerate system, the Accelerate HP, and then on the bottom of the Q series. I probably should flip those, my bad. When looking at the Accelerate here on the bottom, you've got return loss below 10 out to about probably around 11, 12 gigahertz. Maybe if you look at the systems, maybe out to 13, 14. Here, you've got probably out to 26, 27, 28 gigahertz. So because of the newer connect with the better design, we get better return loss performance out to a larger frequency range versus some of the older technology.
A couple of questions.
We'll talk about thumbs in a minute. Sorry, go ahead, Mark.
So just a couple of questions back on that previous slide, and decide whether we've got time to answer them now. We've got about 10 or 11 minutes of presentation time left. What reason would you use different pulse width for insertion loss measurement? So And I guess that comes down to probably frequency components you're trying to.
I'm going to say it depends, right?
Right.
And that's a very general answer to a very specific question. I apologize for that, but the main takeaway from this course is to help embedded engineers understand the SI parameters that are, the signal integrity engineers use on a day-to-day basis to optimize the performance of the electrical system. And it takes experience understanding each of these parameters and how they play off each other to get the max performance through the system. So it really depends upon the customer application in terms of how you design it.
As ever.
I hate to give it probably sounds like a cop-out answer, but every time I go to our signal integrity experts and ask them a specific question, the first words out of their mouth, it seems like always is, it depends. What's the parameters of the entire question? So,
and the questions will be answered in writing as well and circulated to all the attendees today. So there'll be an opportunity to dig into this a bit more and put a bit more meat on the bones when we come back to everybody later in the week.
Yeah, and thanks for that. I apologize. I apologize to whoever answered that question. I'm not trying to ignore it, but it's hard to answer that.
No, understood.
Yeah. So reflection, this talks, we talked earlier about, poor mismatches in the system. Obviously the signal train on the left-hand side, well matched, looks nice. You have a mismatched signal, you can get more noise. So there's overshoot, there's undershoot, there's ringing, and that can play havoc with your receiver depending upon the system design. Some design tips in terms of how to minimize. Again, these are general rules of thumb, right? It's hard to implement these all on every single system, but it helps to keep in mind. On the previous illustrations, we talked about how we look at return loss 10 dB or greater, right? That represents a 10% power reflection, allows for a fair amount of mismatch within the system, and it really depends upon the system requirements. Typically in the digital world, gigabits, hundreds of gigabits, we look at the 10 dB, we look at for return loss over the entire channel greater than 10 dB. And wherever return loss kind of crosses that 10 dB threshold, that's where we kind of say that's the max data rate from that perspective. Now in the RF world, you need a little bit more return loss. So 15 dB because of the requirements for tighter impedance match along the systems. This kind of answers some of the questions that are coming in, that reflections can be dampened by insertion loss. So we may be able to add channel length after the area of mismatch, and that can help to relegate reflections and affect return loss. On the other hand, if there's not enough, but it all depends upon the margins within the system. So if we have a channel margin of 35 dB and we've got insertion loss at only 8 dB, maybe we can go from, if we have a 35 dB insertion loss across the channel and our channel insertion loss is at 28, that gives us a little bit of like 7 dB of room where we can be able to inject some insertion loss to help mitigate reflections. So that's almost why, that's just one example, Mark, of why I almost answer every SI question on, it depends on your situation.
Yeah.
So yeah. On the other hand, if we don't have margin within the system, and if we may not be able to add insertion loss, but if we have good return loss, that may give us a better IL. So this, again, it's all about trade-offs, fine-tuning the system to get the performance you need for your specific channel. Crosstalk, Mark, thank you for, if you and I are both trying to talk at the same time, our listeners would probably go crazy. And that really illustrates what crosstalk is in the audible world. It's unwanted noise. People want to hear you talking. People want to hear me talking, at least hopefully, during this presentation. But if we had a third person talking, obviously that would cause noise on our ears, and it would be harder to understand. When we look at that electrically, the illustration in the upper right of the slide shows what crosstalk is, right? In a single-ended system, I'm putting down a signal down one line, but because of poor coupling or poor isolation, some of that gets coupled onto the adjacent line. This can happen transmit next to transmit next to receive, et cetera, et cetera. And that crosstalk can happen either on the near end or on the far end. So we have near end crosstalk, far end crosstalk. Looking at that from an S parameter standpoint, that would be S13 or S23, very similar to EMI, except it's coming from, instead of EMI coming from the outside world, crosstalk is the noise is coming from something that's adjacent to the system. Question comes up: how much crosstalk can systems handle? And again, it depends. In the digital world, typically 30 to 40 dB. But when you're in the RF world, you may need crosstalk in excess of 70 dB. A good example of that is, one of the trends that we've seen in the industry is the increase in functionality for system design, right? If you think about RF at the system design, you used to have a baseband processor and an RF front end. And the baseband processor handled all the digital, the RF front end handled all the RF. Between the RF signal chain and the ADDs and the DACs, you got everything in the digital world that passed over to the digital baseband processor. Now, with some of the RF SoCs that are on the market, many of these are available through Mouser, all of that scrunched into one chip. So yeah. I've got the RF front end, I've got the RF conversion, the DACs and the ADCs, and they're sitting right next to the digital logic. So the chip designers have done a great job of keeping those parts isolated within the system. But if you look at the front, if you look at the specs for the DACs, the RF DACs and the RF ADCs, the crosstalks are close to 70 dB. So even within next generation ICs, you can see the RF receivers have, they require roughly 70 dB of crosstalk versus the digital SerDes, which are probably 30 to 40 on the same chip.
Yeah.
So these rules of thumb are applicable in embedded designs as we speak.
About 5 minutes, Matt.
Sorry.
If you want to do Q&A.
Yeah, no problem. I'll try to go faster. I'm talking too much. I love this slide because this really illustrates crosstalk, right? You're showing a simple differential pair transitioning from the top layer to the bottom layer through two vias. There's no grounding, there's nothing. And you can see how in the virtual world that noise just emanates across the entire platform. But by putting two grounding vias in, you eliminate the vast majority of that noise. And all we did is we just put two grounding vias from the top to the bottom layer tied into the ground plane on the system. So imagine how much better the performance would be if you actually put those stitching vias or those grounding vias, or you build up a fence around your system, or you ran ground traces right next to your transmission system. So this helps us to see that while a lot of these SI challenges can maybe make us pull our hair out, there's a lot of mitigation techniques that we can use to minimize some of these parameters. So rules of thumb, what are some of the key takeaways? Impedance mismatch is fine if it's within reason. There's no such thing as a perfect match. We talked about all the transitions along a PCB level, along an electrical signal trace can be a transition. It's just inherent within the system design, but we want to minimize it so that it doesn't affect the overall electrical performance. Rules of thumb, we talked about this a little bit, but typical receivers can handle 5 to 7 dBs. Higher-end FPGAs and some of the modern SerDes, when we're talking about gigabits of performance, you can handle 30 to 40 when it comes to insertion loss. When it comes to return loss, 10 dBs or more is good from a digital standpoint, 15 dB on the RF side, and then typically 40 dBs of crosstalk, digitally probably around 70 dB in the RF world. It really depends on the application, the receiver specs. So we have to look at our IC requirements, look at the channel requirements, and simulation is best, as we've shown. Minimizing insertion loss, use better PCB materials instead of FR4, maybe go up to a Megtron or a Tachyon, depending upon the system. Obviously, you have to weigh cost versus your application. There's also the advantage of using fiber technology, take the signals out of the PCB and put them into a twin-ax cable, especially for high-speed digital, and then look to improve the mismatch within the system. Return loss, again, keeping matching is good as possible. If we have some noise budget, maybe inserting a little bit of insertion loss can dampen the reflections. pull pins between adjacent pairs, and then look whether it's single-ended or differential. Crosstalk, we want to keep aggressors away. We'll show an example of how to do that in just a minute. Strip line versus microstrip, so using an inner layer for signal instead of the outer layer. Ground stitching, just adding the vias, adding appropriate grounding throughout the system can actually build a shield within the PCB and within the connector. Pull pins or tie them to ground and switch to differential pairs. Ultimately, tying this all together, it's all about what's the requirements for your system. We can look at PCB stack up. We can look at via and anti-pad design. We can look at what via technology, whether it's through hole, back drilled, even buried, proper routing of the signals, and appropriate guard traces and ground stitching. I'm going to go just 5 minutes longer, Mark, because there's a real world application. We'll allow 10 minutes for answer question.
Yeah.
Yeah.
We've been chatting a long way, so go for it.
Yeah. One of the real world applications where samtec and the industry have kind of all tied this together is around COM-HPC. Getting back to the embedded world, COM-Express is obviously the workhorse of embedded computing design, but it has its limitations. PICMG recently came out with PICMG 3.1 or COM-Express 3.1, which gets the max data rate from PCIe 3 or 8 gigabits up to PCIe 4 at 16 gigabits. That's great. But a lot of the new embedded processors, whether it's x86, FPGA, GPUs, whatever, they're supporting PCIe 5, which gets you up to 32 gigatransfers per lane. So there was a need to move from there was a need to provide a standard solution moving from COM-E to COM-HPC to allow for higher performance, server grade performance for edge computing applications. So COM-HPC does that. Not only are we moving from 10 gigabit on COM-E up to 32 gigabit with COM-HPC, we're also increasing the amount of lanes when it comes to PCI Express, the amount of channels when it comes to Ethernet, and the amount of support for a DDR at the system level. So COM-HPC is not a replacement for COM-E, but it's the evolution for next-gen computing system architectures, really giving server-grade performance on the edge. Now, we make the connectors for it. We're really excited about the innovation that went into these solutions. The COM-HPC connectors use the Accelerate HP connector family from samtec that's available from Mouser. All the technical specs that we've talked about so far actually apply to these connectors. So we're going to tie it all together to show how within the PICMG COM-HPC specification that a technical working group looked at how do I route PCIe 5 from the CPU on the COM module through the COM-HPC connectors down to the COM-HPC carrier card, whether that's off the shelf from some of the embedded board manufacturers that Mouser represents, or if an OEM is designing that carrier card by themselves. So as we talked about throughout this presentation, this technical team led up by Samtec, Intel, and some of the board providers looked at the channel loss specifications for PCIe as defined by PCI SIG, and then applied it to the COM-HPC channels. So again, that illustrates SI performance is really application dependent. So we understand, the technical working group understood the loss budgets for PCIe 5. And then they went about building the channel that would define COM-HPC in a virtual world. So it was building the SI models for the chips. It was building the SI models for the PCBs. It was building the SI models for the connectors. In this case, both the 5mm and the 10mm option that Samtec provides for COM-HPC. It was looking at the SI models of the PCBs, the traces, the via transitions, et cetera, et cetera. So those were built and simulated at the component level, like we just illustrated. And then all those models were concatenated together. And then the channel was built in the virtual world and then simulated. And then tested once all the boards were built. So the nice thing is that, as we'll show in just a minute, all that SI work that went into that drove the design recommendations that are easily found within the COM-HPC design guides available on the PICMG website. So this illustration kind of ties together a lot of the points that we made throughout the presentation. So this is just a small pinout. This is just a small image of 3 rows of the 4-row connector that's used within COM-HPC.
Yeah.
So these are the pins along 3 of the rows. And the green is marked in ground and then signal. So you can think of this as TX plus, TX minus, RX plus, RX minus, TX plus, the whole thing. When this thing was simulated, we assumed it was filled to the max with PCI Express signals running on PCIe 5. You're not going to do that in the real world because there's a bunch of other signals that have to go through the connector, right? The control, the Ethernet, the I2C, et cetera, et cetera. So not every single pin is going to run at 32 gigabit. But by testing it and simulating it with that result, we got the performance that we wanted, right? So some of the key features here too is the spacing on the connector, how the layout was picked, how the pinout was picked, allowed for more density in terms of grounding. Not only could you put the vias right next to the pins, but you could also put grounding vias right next to the ground pins to tie it to the multiple ground planes on the system. And then you could have stitching vias all around the connectors in the rows to help eliminate crosstalk and to simplify the routing of the differential pairs through the connectors. So what's the performance? Let's tie this all together as we kind of wrap up the presentation. We talked earlier about how at the connector level, we typically look at where insertion loss crosses around 1.5 dB. Looking at the insertion loss of just the COM-HPC mated connector pair, both at 5 millimeter and at 10 millimeter, we don't cross the 1 dB insertion loss to about 35 gigahertz. For 32 gigabit PCI Express, PCI Express Gen 5, we look at the Nyquist frequency of about 16 gigahertz. So, here the insertion loss is 0.3, 0.4 dB. Same thing from a return loss standpoint. It doesn't come close to the 10 dB rule of thumb out to about 35 to 37 gigahertz. So again, at 16 gigahertz, we've got more than enough margin to support 32 gigabit per second performance. Okay, so the question comes up, the connector looks great. What about a channel? What does the loss profile look there? So here you can see that the insertion loss is obviously going to be more because instead of going from one contact to the next, now we're going from PCB connector, PCB. Still at 16 gigabit or 16 gigahertz, your loss is less than 1.2 dB. So that gives us design assurance, design confidence that the connectors are going to work at PCIe 5 rates. Same thing on the return loss. At 16 gigabit, we're still greater than 10 dB return loss across the real world channel. So, to me, and we've seen this based on our feedback with embedded designers when it comes to COM-HPC, this is where the SI theory meets the real world in the embedded world. And it shows that the design techniques that data center engineers are using can be applied in the embedded world. And our signal integrity experts are happy to sit there and work with anyone to find the right solution for the right system. So key takeaways: we have a global team of SI experts, online design tools, and world-class customer service to answer any SI question, especially in the high-speed embedded world. Our SI engineers are located globally, Mark, in all 3 key regions of the world: Asia Pacific, EMEA, North America, and we're ready to support our teams. We offer a comprehensive portfolio of interconnect solutions, ideally suited for high-speed embedded applications such as COM-HPC, which we mentioned. By the way, our COM-HPC connectors are available through Mouser. And we've also come out with a new resource, our Signal Integrity Handbook, that we make available complimentary to the industry through Mouser, directly from Samtec, that continues to build upon the basics of this webinar to deepen any engineer's understanding of SI basics. For more information, you can visit the Mouser landing site for Samtec, mouser.com at Samtec. Sorry, mouser.com/Samtec, or you can email us at sig@samtec.com. So let's try to cover those questions, Mark, as best we can.
Yeah, thank you. Yeah, we've got a few minutes left, and thanks for the overview. It's clearly a complex topic area, and needs system level consideration. Pavel has still got his question out there around the kind of board to board connectors, and I guess you've touched on some of that depending on the application with COM-HPC.
Yeah, so let me just answer that. So Pavel's question is really good. What do we have at 1 megabit? Honestly, at those types of data rates, you can use traditional board-to-board headers, 2.54 millimeter interconnects, with a relatively small stacking height, and still get the 1 megabit performance.
Right.
If there's questions specific, well, I'm using this type of protocol, I'm using singlet, I'm using differential, whatever. Pavel, I'll respond to you directly once I get your contact information afterwards, and I'll get you in touch with the right technical resource to help you work on your specific application after the webinar. But great question. Thank you for that.
Yeah, we'll answer all the questions in writing, so you'll be able to point them in the right direction, Matt. Questions around like bit rates and Nyquist. I guess for decent signal, you usually need more than 2 times bit symbol rate. And I guess I'm not quite clear there what that was getting at. I think that was a little while ago in the presentation when we were talking about Nyquist and bit rate. Yeah,
no, it's a good point, right? We talked about the theoretical, right? If you're talking about bit rate, if you're at 100, I'm just pulling numbers out of the air. If you're running at we'll call it a gigabit per second, right? You need to have a Nyquist rate of at least 2 gigahertz, right? 2 gigabit. But in general, you want to have more, right? Because that provides more margin for the system. So he's exactly right, right? And the big reason too is not all the energy for the signal is going to be at Nyquist. You're going to have energy for the signal at the second harmonic, third harmonic, et cetera, et cetera. The design of this, or the goal of this webinar, Mark, though, is to try to mitigate where all that energy is and try to get it on Nyquist as much as possible, right? We had a ton of more, in the data that we showed here, just to illustrate it one more time. In the data that we had here, I'll just use this for COM-HPC, right? We're worried about 16 gigahertz Nyquist for 32 gigabit data rates. We got a ton of margin out here, probably out to about 25 to 30 gigahertz, right? It's not like at 16, it just falls off completely.
Yeah.
So there's margin there. So the point there that was made by the listener is spot on, right? That margin gives us confidence in the system in case something happens. The contacts become loose. You still get performance before there's a failure. So yeah, great point.
Again, what's clear, I think, is you've got to consider each like any design from any perspective. Really, it's all about the system and the overall application. One last question, as we're going to run out of time. Rob was talking about insertion loss, saying it's due to poor impedance matches, or is it correct that it's due to poor impedance match? And I think we've touched on that a few times now. Yeah,
the mismatch is a great contributor to insertion loss on short traces. It's not the only one, or it's not potentially there could be crosstalk, there could be bad grounding schemes, et cetera, et cetera. So Mark makes a good point that the mismatch for short traces does contribute greatly, but there's also other influence as well.
Yeah, and again, system. Think about the overall system end to end. Okay, we've run out of time, Matt. Thanks very much for your time and effort in putting this together for us, and certainly for highlighting where people can go to get further information. What I will say is, the archived or on-demand webinar will be made available to everybody. We will answer all of the questions we've received in writing, and they'll be circulated to all the attendees along with any supporting information. At the end of this webinar, there will be a survey, so we'd appreciate if people would take a little bit of time just to help us to give some feedback and help us improve future webinars. But thank you again, Matt. Thanks to everyone for joining, and look forward to seeing you all on the next one. Thanks very much.